Okay, let's move to the inductors. Inductors. So, inductor is actually kind of a coil. So, what we simply do is we feed a current, and this particular inductor coil has N turns, and depending on the current flow through this inductor, so there may be a voltage induced across this coil. So, ET. So we know that if we feed a current to the inductor, so due to this arrangement there is a flux generate across this coil. So this is called as flux linkage. This is called as flux linkage. So the total flux is actually equals to the flux generated due to a coil into the number of turns. So this is the flux generated due to coil, flux per coil or flux per turn, and once we multiply it with the number of turns, so you can easily find the total flux generated by this current or the flux linkage due to this current. So then we can simply define a total flux or the flux linkage as a product of phi into n. Okay, so again, like if we precisely explain this or define this, we can simply say that so this lambda t, so which is the total flux linkage due to this current it, is actually this, because this flux is induced due to the time varying current. So this is a kind of a flux which is depend on the current what we feed to the inductor. So then the total flux linkage is again a kind of a time dependent variable. So this is time dependent variable. So the total flux linkage is actually flux per turn into the number of turns. So again, like for the linear inductors, so we know that the total flux is actually proportional to the current feed to the circuit. So we know that the total flux linkage is simply vary with the current we feed to the inductor. So this relationship between the current and the induced flux is this. So the total flux induced across this inductor is simply proportional to the current flow through the inductor. So this proportional coefficient is actually called as the inductance of the coil. So this is basically measured in Henry. So the inductance of the coil is measured in Henry, and for the linear inductors, linear means the induced flux is simply directly proportional to the current we fed to the circuit. So this the proportionate coefficient would be the inductance of the coil, which is measured in Henry. So now we know that, so we have a kind of a relationship. So the total flux or the flux linkage is equals to L times IT. So if you simply differentiate these both things with respect to time, so we have this lambda t over dt equals to L dit over dt. So we know that, so due to this flux change, so we have a kind of an induced voltage across the inductor. So if you have a time varying flux, so we know that there is a voltage induced across this inductor. So then we can simply rewrite this entire equation. So the induced voltage is equals to L times the derivative of the current. So this is the induced voltage. So this is the induced voltage. Induced voltage. So this is the rate of change of current. So this is the important equation which we need to highlight it here. So the induced voltage across the inductor is equals to the L times the derivative of the current. So this is the fundamental equation for the inductor. Similarly, we made a kind of a similar type of equation for the capacitor. So it's something like that. The induced current is equal to C times the derivative of the voltage. So for the inductor, so the induced voltage is equals to L times the derivative of the current. So this is the fundamental equation which we need to keep in mind. So let's see what we can get it from this particular equation. So this is the equation. So what about if this IT equals a current, kind of a constant current. So then, so VT should be equals to L times the derivative of this current. So now the current is a kind of a constant which leads to a zero voltage. So then if you have a kind of an inductor here, and if you inject a constant current or DC current, so there won't be any voltage induced across this inductor. So VT is simply 0. So then we can model these inductors when we are dealing with DC quantities as a kind of a short circuit element, because so across this inductor there won't be any induced voltage. The voltage drop across the inductor is 0, so inductor acts as a kind of a short circuit element. So this is only valid for when the current is a kind of a constant. So if we are dealing with DC quantities, so inductors can be simply replaced with the short circuit element. So this is a one important thing. If your I current is kind of a DC quantity, you can replace the inductor with a short circuit element. So what happens if we apply this kind of a current variation? So this is the current P fed to the inductor. So at t equals like this is like t equals 0. So the derivative at t equals 0 is kind of infinite. So then the induced voltage across the inductor for this particular case is infinity. So this is again, it's not practical and not possible in the practical circuit, because we basically feed power to the circuit through a kind of a finite source, finite DC source or finite AC source. So if we apply this kind of a variation to the inductor, so we know that the voltage induced is something like that. So at t equals 0, you have a kind of a infinite induced voltage, or the otherwise the derivative would be 0 and no induced voltage across the inductor. So this goes to infinity in mathematical aspects, but practically it's not possible, and this V basically goes to kind of a V max, maximum voltage, which this external source can accommodate. So we know that this once we apply this kind of a sudden current change to the inductor, so the derivative would be infinite and the induced voltage becomes a kind of a infinite. But in practical circuit, so we basically power up the circuits through a kind of a finite DC or AC sources. So then it's not possible to boost the voltage to infinity. So anyway, in those places we can observe kind of a sudden spikes which bring the voltage to its maximum. So then to for these inductors we basically assume that these inductors cannot handle this kind of abrupt changes, this kind of a sudden rises or sudden drops or falls. Okay, because once we apply this kind of a sudden rise or fall through the inductor, so then the induced voltage becomes a very large value, so then the rest of the circuit cannot tolerate that kind of a very large induced voltage, so then it's not possible. So then as a conclusion we made two. One is like for DC current, inductor can be replaced as a short circuit element for DC current, and inductor cannot operate during this kind of sudden falls and changes, because the derivative of this current for these two places is actually infinity, and the induced voltage becomes infinity then. Okay, so this is basic. So this is one fundamental equation is this. So from this we can obtain a relationship for the current. So if you cross multiply this equation and integrate it to both sides, so we can have this kind of equation. I becomes 1 over L integral of this voltage. So we can treat this integral as very similar to the previous case which we discussed in the capacitors. So then this current can be precisely write it in this form: 0 to t V tau d tau plus this. So this is actually the initial condition. This is the initial condition of the inductor, which captures the, which basically captures the this effect. So what happens from the past up to a present is basically captured through this initial condition. So initial condition itself gives a kind of a clue about the behavior of the inductor during this past. So that's right. So this basically capture the trend during this future. So if you want to evaluate the current flow through the inductor, so this is the simple equation. So 1 over L, this is the constant for the given inductor. This is the inductance value of the inductor. See, in integral of the voltage from 0 to t, t is a kind of a time varying quantity. So which may be like 1 second, 2 seconds, 3 seconds, or kind of again t, and the initial condition until 0. So keep in mind all the ways. So if you put 0 here, so we should capture the history up to that value. So 0 should be here. For example, if you generalize this, so it's something like that. Okay. So if you simply consider the history up to minus infinity to a, so then this integral counts from a to t, and this initial condition should simply embed the information from minus infinity to a, not for 0. So keep in mind, so whatever the quantity you put it here, exactly here. So this integral value is for a to t. So then you should capture the behaviors from minus infinity to a through this initial condition. So once this a equals to 0, so you can easily derive this equation. So then 0 to t plus the initial condition up to 0. So these are the two fundamental equations. So this is the relationship between the voltage and current. So we can take the expression for the current like this. So it's basically 1 over L integral of the voltage from 0 to t plus the initial condition or the initial current of the inductor. So we'll take one example to understand it properly. So I'm referring this exercise 1, which is in the slides I gave to you. So here you are given a kind of a plot or the graph which shows the voltage variation along with the time. So it's a kind of a square wave type of trend. So from 0 to 1 the voltage would be plus 5, then 1 to 2 it's minus 5, then again plus 5, again minus 5, like a, it's a kind of a periodic square wave uh, operate between plus 5 and minus 5. So this is the voltage variation across this or inductor, or the induced voltage across the inductor. So it basically gives that the inductance of the coil as half Henry or 0.5 Henry, and So this it's basically gives another factor for 0 to 2 second. So the initial yeah, so the find the current in point 5 inductor for 0 to 2. So we need to find the current between this period between 0 and 2. So you need to find the current between this t to 2 second, and it was given that the initial condition up to 0 is equal to 0 amperes. So voltage of the in this voltage across the inductor is given as a kind of a periodic square pulse, square wave, which operates between plus phi and minus phi, and we are asked to evaluate the current variation, or the we are asked to derive the expression for the current between 0 and 2. So if I draw the pattern, it's something like that. So this is 1, so this is 2, this is minus 5, so this is plus 5, this is the voltage variation. So from the basics we know that the induced current is equals to 1 over L A to T V tau d tau plus I A. So this is the fundamental equation which we obtained previously. So to find the current, we need to evaluate the integral, and by looking at this one, so we know that this voltage is a kind of a, so Vt is actually a piecewise continuous function. So this is not a continuous function like this between 0 and 2. So it's a piecewise continuous function. So between 0 and 1 the value of the function is 5, and from 1 to 2 the functional value would be minus 5. So this is a kind of a piecewise continuous function. So if it is a piecewise continuous function, so we cannot apply the integral directly. So you have to partition the function based on the continuity, and then we have to apply the integration. So by looking at this voltage variation, we can simply partition the function like this: 0 to 1, and then from 1 to, yeah, or equals to 2 or not equals to 8. So anyway, we need to partition this function into two blocks. So we have to capture the current variation between 0 and 1 and 1 and 2. So we cannot just evaluate the integral from 0 to 2 because it's a piecewise continuous function. Yes. So then, so first we consider that t is in between, so during this interval. Okay. So then we can find the value. So t is in between this. So then we can simply say that it equals 1 over L means 2 times 0 to t v tau d tau plus I0. So this is the integral expression which explains the current behavior during this interval 0 and 1. So keep in mind we will put a kind of a random variable t here, because once you put the integral from 0 to 1, it basically gives the current at t equals 1. So if you just do this in evaluation, 0 to 1, 2 times the I0, so this gives the current value at t equals 1. So what we want is we need to capture the current variation between 0 and 1, not only the current at t equals 1. So that's why I put a random value t here, which is actually in between 0 and 1. So once you evaluate this integral, it gives a kind of a indefinite expression which is depend on t. So then by changing the t, you can easily get the understand about the complete behavior between 0 and 1. See how we can do it. So during this 0 and 1 period, we know that the voltage is plus 5, so then this becomes plus 5. So I0 is given as 0. So then this integral is simplifies to this 2 times 0 to t 5 d time. So then this becomes 10t. So see, so it's a function of t, because we introduce a kind of a random quantity to the upper limit of the integral. So then we'll ended up with a kind of a time dependent function. So this is the current variation between 0 and 1. So once you substitute t equals 0, the current is 0. Once you substitute t equals 1, so this current is 10 amperes. So in between 0 and 1, so the current variation is like linear between 0 and 10. So if you draw it, so it's something like that. So between 0 and 1, so initially the current is 0, and here its current is 10 amperes. In between that, it's linear, and the functional definition is 10 times t, 10t. So this is the current variation. So if you just put the upper limit as 1, you just capture this value only. So you cannot find the trend in between 0 and 1. So that's why we put a kind of a random variable t in between that. So then what happens, like for the next case? So if we consider this, so then it again 2 times. So this is basically goes from 1 to t. So now this t value is in between 1 and 2. So the integral goes from 1 to t. Now t is actually in between 1 and 2. V tau d tau plus. So the initial condition would be I1. So the initial condition at t equals 1 second. So how do you get this? So from the previous equation, so from the previous we obtain this relationship. So from this one you can easily get the value for t equals 1 case. So it's almost equals to 10 amperes. So we know that for the inductors we cannot have this sudden changes in the current or voltages. So we can assume that this is true. I 1 minus equals I 1 plus equals I 1. So it means like so this is t equals 1. So the current which is very near to this is I1 minus, and this is I1 plus, and the exact value at t equals 1 is I1. So these are equals, because these capacitors and inductors cannot manage this sudden changes, sudden rises or sudden falls or drops. So then we can assume that during these kind of places it's like continuous. So then t equals 1, so this value, these three values are coincident and the exact. So it's here. Similarly for voltages in capacitors also we can build the same argument, because for the inductors we argue that so this cannot be managed, this these kind of situations cannot managed by the inductors. So it means like at any given time, so the variation of the current variation of the inductor should be kind of very smooth. So this kind of situations were not observed in the variation of the current in the inductor. So then we can basically assume that this is a valid argument. So for any t minus equals to I t plus equals to I t0. So the current value at t equals 0 is exactly equals to the current value at I t0 plus and 0 minus due to this. So these inductors cannot manage this kind of a sudden variation in their current. So the definitely the current across the inductor would be a kind of a smooth continuous function. So then this is valid. For the capacitors we can similarly build like Vt0 minus equals Vt0 plus equals Vt0, because for the capacitors we know that capacitors cannot handle this kind of a variation, voltage variation. So again for capacitors, so the voltage variation across the capacitor plate should be kind of a smooth and continuous, smooth and continuous. So these two are valid for, this is valid for the inductor, so this is valid for the capacitor. Done. So from this one we can simply say that this is equals to 2 times 1 to t. Now the current between 1 and 2 becomes plus, sorry, minus 5 d tau. So the initial condition at t equals 1 is 10. So once you substitute it here, so you have 10 times t minus 1 plus 10. So it becomes 20 minus 10t. So this is the current variation between this. So if you summarize this, so current equals 10t during this and 20 minus 10t during this. So once you plot it here, between 0 and 1 the trend would be linear, so it's something like that. So at t equals 1, once you substitute it here, so you can simply say that the current is 10. So then at t equals 20, current is 0. So definitely it should be kind of this. So the mathematical trend between 0 and 1 is 10t. So this is like 20 minus 10t. So this is the variation between 0 and 1, this is the variation between 1 and 2. The entire distribution of current between 0 and 2 is this. So you cannot just write this equation 1 over L 0 to 2 b tau d tau plus I0. So this is not a kind of a logical statement, because this v is a kind of a piecewise continuous function, and definitely you need to put it into the function to partitions or regions. So one region would be this, the other region would be this. So likewise you can continue this question until you get the current value at t equals to 4. So then you have to partition it from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And in bit, if you want to evaluate the trends in between this region, so keep in mind your upper limit would be kind of a random variable. So if you just put a constant here, it basically gives the value at that particular constant. So if you want to get this kind of intermediate trends, so you have to put the upper limit to the random variable. So then you can basically refer the slides for the series type of inductors. Once the inductors are in series, what would be the equivalent inductance, and if you put the inductors in parallel, what would be the equivalent inductance for this parallel combination. So like in the resistors, so you can build a similar type of arguments or and come up with a kind of equivalent set of values. So if you know these two, you can basically simplify the combinations by looking at whether they are in series or they are in parallel, and then you can simplify the circuit to a single inductor or capacitor. So if you have multiple inductors or capacitors in the circuit, by identifying the series and parallel combination, you can basically simplify the circuit to a single inductor or a single capacitor. So then you can basically manage the rest. So this exercise 4 is basically capture that. So you have 5 inductors. So these last two 1 Henry inductors are in series, so you can treat it and find the equivalent to replace these two series 1 Henry inductors. So then whatever the equivalent you obtain is basically parallel with 2 Henry. So then you can basically treat them for as the parallel inductors and find equivalent. So then whatever the equivalent would be series with this 2 over 3 Henry one, so then you can treat it as a series combination and find the equivalent. Then ultimately, so it should be parallel with 5 over 2 Henry inductor. So then you can completely replace this 5 set of inductors and the series and parallel combinations into a single inductor which is in series with the current source. So then you can basically apply whatever the basic equations. So during this discussion, so we can basically summarize these two. So this is the capacitor, so this is the inductor. So for the capacitors, the induced current across the capacitor is equals to C times the derivative of the voltage, and voltage can be easily find out from this: A to T I tau d tau plus VA. And for DC voltages, so this becomes a kind of a open circuit, and For the capacitors, voltage should be this kind of VT should be continuous, and this is possible. So this is possible. For the inductors, the inductance of L, induced voltage across the inductor would be equals to the L times the derivative of the current. We can easily evaluate the current across the inductor from this integral. And for constant current, so the induced voltage is 0, so we can simply replace the inductors with short circuit element. And for inductors, current should be continuous and smooth. So then this is basically true. So this is the summary of this capacitors inductors. So I am not dealing with this any physical stuff. So the entire idea of the circuit analysis 2 is to model these capacitors and inductors, and this model can be applied to analyze a circuit. So that's why this focus is completely to the mathematical form. So for the capacitors and inductors, so these are the very preliminary type of equations you can derive it. So these two are the fundamentals. If you know this one, you know this one. So if you know this one, you can simply derive the rest. So if you know this, you can derive the rest as well. So nothing to worry. So you need to keep these two in mind. So if you know this one, so any kind of modeling can be possible. Okay. So we'll then next time we'll move to the first order circuits.